Okay, then let's start. Okay, yeah, my name is Carsten Einwich. I'm chairing this session. This is in the second stream. It's mainly dealing this session with digital design with one focus on high-level synthesis. Yeah, we have now the first presentation from Preetham. Is this correct? Correctly? Yeah, and
Yes,
then let's
Carsten.
start. Let's start.
Hey everyone,
The video
I'm
is
Preetham
used.
from
Okay, sorry. Start. Yeah.
the System LSI team at Samsung Semiconductor India R&D, and I'll be presenting the work done earlier this year by my colleagues Surendhar, Ashwani, Youngchan, Youngsik, Brian, and myself on achieving faster code coverage closure using high-level synthesis. The agenda of this presentation is as follows. We'll first talk about high-level synthesis and give its advantages and disadvantages when compared to the traditional RTL design flow. Next, we'll give an introduction to code coverage with the HLS flow and give an idea as to how difficult it is to achieve this right now. Post that, we'll talk about some commonly used terms in the code coverage parlance. Next, we present the crux of this presentation, which is our HLS code coverage closure flow. This is a set of tried and tested guidelines we used at Samsung in order to achieve faster code coverage closure using HLS. Next, the experimental results on a Samsung 1.3 million gate IP design showing that the code coverage closure flow works well is presented. And finally, we present inferences drawn from this research work and conclude our presentation. In this slide, we introduce high-level synthesis and provide its advantages and disadvantages. So in the past few years, there actually has been a significant traction in using high-level synthesis to design IPs in both the industry and academia. Increasing complexity in system architecture and faster time to market constraints are forcing design houses to move to higher levels of abstraction. HLS EDA synthesis tools are more robust than before, and system level design using System C help in coding algorithms or designs at a higher level of abstraction than the traditional RTL method. System C combines the best features of the object-oriented C++ language along with hardware description constructs, thereby making it well suited to describe designs at a higher level of abstraction. HLS is the process of transformation of a design at a higher level of abstraction, typically written in either C, C++, or System C to RTL, which is nothing but your Verilog or VHDL design. The figure depicted here is the typical HLS flow. The System C design, as in our case, along with a process node technology component library and constraints directives like what the area should be, what the latency should be, what power constraints should be, are some of the inputs that are given to the HLS engine, and the output of this HLS engine is nothing but synthesized Verilog and VHDL code that best satisfies whatever constraints and directives have been given to the HLS tool. So that's HLS in a nutshell. We are not going to get into how the transformation actually happens, which is nothing but a series of algorithms. but this is just the overview of what HLS is. HLS helps in quick turnaround of design changes and allows for design space exploration and trade-off among various configurations in regards to the area, latency, and power constraints given. Design respins using HLS take much lesser time, and engineers can actually focus on the design work while the EDA tools handle the implementation specifics. However, HLS tools are still not fully automated and require the designer's inputs to guide the tool in arriving at an optimal solution. So this is the disadvantage of the HLS flow, but since the advantages far outweigh the disadvantages, HLS is popularly used in designing today. This slide talks about code coverage in a typical high-level synthesis flow. Closing code coverage as part of the HLS flow is extremely difficult. A literature survey done, which was across many papers, did not yield any good results on a clear-cut procedure to follow such that code coverage closure is achieved as part of the HLS flow before RTL sign-off. Closing code coverage earlier in the HLS design cycle would lead to a reduction in the regression runs, testing, and thereby consequently reducing CPU usage as well as simulation tool licenses consumed. Our research work attempts to provide a set of guidelines for designers to achieve code coverage closure in a structured manner before RTL sign-off. It also helps reach code coverage closure faster than the traditional methods followed. Right now, I think people do most of the HLS code coverage at the RTL level. So that's something that we have tried to improve upon. And this approach is an optimal mix of code coverage measurement that spans across both System C and RTL levels to achieve coverage closure. These guidelines are EDA tool vendor agnostic and have been tested out on a Samsung multimedia IP design that actually synthesizes to about 1.3 million gates. This slide and the next talk about terminology used in code coverage measurement. Code coverage is a measure of the percentage of the design source code executed by running tests via regressions and applying various input vector combinations. There are various measurement metrics that constitute code coverage, and those terms are actually explained in this slide and the next. The first is line coverage. This is a measure of all possible executable lines of code in the source code that have been executed at least once. It ensures that each line in the design source is covered at least once by the tests that have been run. The next term is function coverage. So this measures the extent to which functions present in the source code are covered during testing. The purpose of this metric is to ensure that all the functions in the design source have been called, because depending on the combination of the input values used, a function may or may not be called during execution. The third is condition or expression coverage. Whenever there is a condition in the source code, its evaluation would result in a Boolean value of either true or false. Conditional coverage looks at all Boolean expressions and counts the number of times it was either true or false. The fourth metric is block coverage, and this is a measure of which blocks in the code have been executed and which have not. On this slide, we continue with more terms used in code coverage measurement. Branch coverage. This looks at all the conditional branching statements, if then else and case branches, and counts each branch taken. The next metric is statement coverage. This is a measure that provides information whether or not all statements within a block have executed. Next is toggle coverage. This is a measure of the activity, that is the value change either from 0 to 1 or from 1 to 0 of various signals in a design. It provides information on untoggled signals, that is signals that actually remain constant during a simulation run. And finally, we have finite state machine, FSM coverage. So this is a measure of what states were visited in the FSM and which transitions were taken. So things like state coverage, transition coverage, and arc coverage are some of the measures that constitute FSM coverage. This and the next few slides talks about the HLS code coverage closure flow that we have developed. Closing code coverage earlier in the HLS flow is extremely difficult, and there isn't any well-defined procedure to achieve this before RTL sign-off. It is impossible to completely close code coverage at the system C level. If one closes coverage at the system C level, then there's no support for things like toggle coverage, FSM coverage, etc. And completely closing code coverage at the RTL level would increase the turnaround time in rapidly respinning designs using HLS. Hence, we devised an approach which is an optimal mix of the code coverage measurement that spans across both system C and RTL levels to achieve code coverage closure. The figure shown here is a flow diagram of the proposed HLS code coverage methodology. It consists of 5 steps, and these are explained in detail over the next few slides. So step 1, make use of any code coverage tool that supports condition and decision coverage to achieve 100% code coverage on the system C design. Use the minimal set of tests from your regression suite to achieve this 100% code coverage. Now this ensures lesser testing coverage measurement at the RTL level. Our experiments have shown that Bullseye covers code coverage better than GNU's GCOV tools. GCOV covers only line and function coverage with no support to measure condition or decision evaluation. It also does not provide any option to exclude pieces of code from measurement. Bullseye alleviates these problems listed with GCOV. While doing our experiments, we actually found things that are useful for designers. So these are listed in this presentation as tips. So tip 1. There is a possibility that system C code coverage tools might have their limitations even though they report 100% code coverage. Our experiments using a system C code coverage tool showed that 100% code coverage was achieved even though it didn't cover bitwise logical NOT and relational operators in the right hand side expression evaluation. Take this for example. The NOT as well as the AND on the RHS is not covered. Take another example. The tool that actually gave us 100% code coverage did not cover all the array elements on the right hand side of an expression. So from this example, just one index value is enough, and the code coverage tool showed that this statement is 100% covered. So the important point to note here is that not all of the array indices have been tested. So this system C code coverage tool reliability factor is yet another important reason that code coverage closure has to be finished at the RTL level. This slide explains step 2 of the code coverage flow. Once synthesis is performed, run the same minimal set of tests as described in step 1 on the synthesized RTL code. Measure RTL code coverage using your favorite code coverage tool. Exclude measurement of toggle coverage here, and the code coverage achieved will still be less than 100%. This is because the synthesis tool adds extra RTL components for things like pipelining and stall architectures, implicit else or default branch statements, unrolled loops. So here parallel copies are made in the hardware, FSMs, external memory structures, first in first out buffers, math functions, and other structures from the tool vendor libraries. Typically other synthesis tool directives as well. All these new RTL code constructs will have to be covered at the RTL level only. It is possible for the synthesis tool to generate a few efficient RTL structures by specifying synthesis coding directives and options, but majority of the RTL code generated cannot be easily correlated back to the system C design. This figure shown here gives an example where direct correlation back to the system C design from the synthesized RTL is difficult. If you actually see, this is an array access, and the equivalent RTL code for that is some sort of a case based structure. So it's not very easy to comprehend how one gets converted to the other. That's what we are trying to explain here. This slide gives details about step 3 of the code coverage closure flow. It is possible that some of these new RTL constructs are just dead code and might not be reachable or sensitized from the inputs. So use your favorite formal verification tool and run the unreachability analysis on the synthesized RTL code. Our experiments have shown lots of unreachable code and states in the RTL design. So these formally unreachable code segments and states need to be excluded from code coverage analysis. A tip for designers from our experiments: we suggest increasing the prover time to a much larger value than the default in the formal tool for running unreachability analysis. This is because there are chances that the tool might return many undetermined cases due to insufficient default runtime provided. During our experiments, we found that the formal tool we used had a default prover time of 8 hours. So changing that default value to a larger value helped the tool cover all undetermined cases found in the previous default run. This slide gives details about the final 2 steps of the code coverage closure flow. In step 3, we have already excluded the unreachable RTL code. Hence, in step 4, first identify and then add tests to cover the remaining new RTL code constructs present. This will complete code coverage for the RTL design with the exception of toggle coverage. Finally, in step 5, add tests to cover the toggle coverage holes that remain. Once this is done, code coverage will be at 100% and the RTL design can be signed off for the backend design flow. Experimental results are presented from this slide onwards. A Samsung multimedia IP design was developed using HLS. The original System C design had 6,980 lines of code, while the synthesized RTL design contained 356,959 lines of code. And finally, this translated to a 1.3 million gate sized design. The 5 steps of the code coverage closure flow previously explained were applied on this multimedia IP, and 100% code coverage was achieved as follows for each step. Step 1. The bullseye tool was used to measure code coverage of the System C design, and 69 tests, which were the minimal number, were actually used to achieve 100% code coverage at the System C level. Figure 1, which is this, shows the various code coverage aspects of the design measured at the System C level. So it shows that the multimedia top as well as all subsystems below it are 100% covered. Function coverage is at 100%. Nothing remains to be covered with regards to functions. Similarly, condition decision coverage is at 100% and nothing is uncovered. Step 2. The same minimal number 69 tests run at the System C level now are run on the synthesized RTL design and code coverage measured. Toggle coverage was excluded here, and the blue rectangle seen in this figure shows that 96.77% code coverage was achieved on the RTL design. So this is the 96.77% that can be seen in step 2. We continue with experimental results on this slide. Step 3 of the code coverage flow was applied on the multimedia design. Formal unreachability analysis was run on the RTL design, giving the prover a time period of 36 hours. The Jasper run log seen in the figure shows that 112 out of a total of 15,248 blocks are unreachable. Only 15,136 blocks were able to be reached. So the unreachable code blocks are excluded from the RTL code coverage measured, and coverage metrics in the blue rectangle seen here show that 96.80% code coverage was achieved on the RTL design after excluding the 112 unreachable code blocks. This slide gives the results of the last 2 steps explained in our methodology. Step 4 of the code coverage flow was then applied on the multimedia design. A careful analysis of the new RTL code constructs was done, and 47 more tests were added to cover them. The blue rectangle in the figure shows that 100% code coverage, of course excluding toggle, was achieved on the RTL design after adding these new tests. However, the overall code coverage including toggle coverage seen at this point is still only 94.71%. The final step, that's step 5 of the code coverage flow, is now applied, and this involved adding 13 tests to cover all the toggle points for the design. The blue rectangle seen here in this figure shows that 100% code coverage was achieved on the RTL design after adding these new tests and all the toggle bins were hit. The conclusions and inferences from our research work are enumerated on this slide. We have defined a complete and comprehensive methodology agnostic to EDA tool vendors, which achieves code coverage closure earlier in the HLS design cycle. Code coverage closure was achieved 22.2% faster on a 1.3 million gate Samsung multimedia design with these guidelines when compared to the traditional HLS RTL sign-off flow. Learnings from our experiments with various tools during this exercise have been provided as useful tips and information pointers as part of this presentation as well as the final paper for practical use during the HLS design flow. The HLS code coverage guidelines described here are ready to be deployed across various design teams throughout Samsung. The references used in this presentation and the paper are listed on this slide. We'd like to acknowledge and sincerely thank the Cadence HLS team comprising of Vijay, Mike, Jingru, Lokesh and Jongchul for supporting the Samsung IDT-DM team with the Stratus toolset. Thank you for your interest in our presentation and for attending this session.
Okay, thank you. There are any questions? Please use the chat. Okay.
In fact, I'd like to probably add something if there are no questions. We got feedback as part of this paper review, and we're currently working on that. So the feedback given was to actually look at symbolic execution for creation of minimal tests. So we're currently looking at that. There are the CLI environment from Stanford, and there are a few others that are there. So we currently are looking at that and trying to see whether we can actually integrate that and create the minimal test. So there are some questions here.
Yes.
When some
Yes.
RTL line isn't covered, isn't it extremely hard to find out what that line does? So absolutely, you are really correct about that. It is very, very difficult to find out what exactly that line does. So you typically have to go back and kind of correlate it to what in the system C design caused that RTL to be generated. And the tools that we actually used Cadence's Stratus tools. So there is a way of kind of correlating it, and you can annotate, the RTL gets annotated with what the corresponding code in system C is. So using that to an extent, you can find out what that line does, but it's not always the case. It's very difficult. And
Hello.
okay, so the next question was, have you been able to apply this to larger designs? So the question basically is, have you been able to apply this to larger designs? We currently are using this on different Samsung IPs. So yes, we are looking at larger IPs, and we have been able to apply this methodology to design from the sensor team. So it is a much bigger IP, and they currently are in the process of using this to close code coverage and get their design up and running. The third question is, have you tried the RTL annotation feature to add reference to system C code and the system C source? So yes, we definitely have done this. It's like how I explained before. Cadence's Stratus tool does the RTL annotation, and you are able to see certain lines of code which kind of correlate from your system C to RTL. But it's okay. It's not very how do I put it? It's useful to an extent, but it does not solve all your problems.
Okay, then thanks a lot, Preetham. Usually we would have now applause, but it's a little bit difficult in the virtual conference. Okay, then let's go to the second presentation. It's from Kaushal. Yeah, and
Thank you.
Yes, thank you also. Then I don't know, do you do it live, or is it also the video should be played?
Okay, hi everyone. Let me share my screen.
Okay, you share your screen, make it live. We see your screen, but not the slides yet. Okay, now, yeah.
Okay, great. Okay, so hello everyone. My name is Kaushal Shah. So I'm a senior R&D engineer with Siemens CDA. So I mainly focus on the development of static and formal verification tools with the team. So I did my post-graduation from IIT Kharagpur in VLSI design. So for today's session, I'm going to present you a novel methodology for detection of glitch-prone clock and reset propagation using the automated formal analysis. So let's start with it. Okay, so enough has been said about like how important it is to identify bugs or issues earlier into the development chip development cycle. And we all know that the pressure and the stress keeps on mounting as we reach near to the tape out deadlines. So once, let's say you have your RTL verification done and you are now ready with your RTL sign off, but it may happen that later at the design stage, due to the synthesis process, you may introduce some kind of issues. So I will just tell you about first the clock domain crossing verification that we do at the RTL step. So clock domain series verification is a critical step in the design verification of a cycle. Series verification ensures that the signals pass asynchronous clock domains without being missed or causing metastability. Traditionally, series verification is done on a register transfer RTL representation of the logic of the design. However, during the synthesis stage, when the design is transformed from RTL to gate level, some issues like glitches can be introduced that may eventually lead to the chip failures. So even after RTL series verification closure at the RTL stage, it is important to perform series verification on a gate level design to detect and address new issues. So we conclude that we want series verification done at the gate level design so that the issues introduced maybe at the synthesis stage can be addressed. Okay, the next slide tells about like how the changes introduced in the netlist during the synthesis can lead to potential issues. So the changes introduced in the netlist during the synthesis, such as the timing optimization of synchronization logic and insertion of design for test logic, may cause incorrect behavior in CDC synchronizers, or introduce new CDC paths, or can break the valid CDC paths. So here we are showing you a valid demux crossing. So this is an RTL representation of a valid demux crossing. And during synthesis, it may be mapped to some generic technology, but to meet some design constraints of area, power, or timing, this will be mapped to some targeted technology, and the optimizations can be done by the synthesis tool. By this, when these optimizations are done, it may happen that some logic can be introduced or some logic can be removed to meet those constraints. Now, the introduction of the new logic or the removal of the new of the logic can create additional CDC paths or may break the valid CDC paths. It can also introduce an issue known as glitch. This presentation will mainly focus on how the synthesis introduces the glitch in the design and how we are going to detect it. Okay, so the question that we raised here is, what if the synthesis optimization introduces new issues in the gate level design? Okay, so we know that now the synthesis step that does some optimizations to meet the timing or some other design constraints, it may introduce some issues known as glitch. Now let's understand what are the glitches. Glitches are unwanted spikes in signals that can propagate through the combinational logic. At times, signals display an incorrect intermediate value before reaching the final steady state value. Now this results in a glitch. Glitches are mainly classified into three categories. The static zero glitch. By static zero glitch, what we mean is the signal is meant to be held stable at value 0, at value steady state value of 0, but due to some issue, it will momentarily go to value 1 and then again reach to value 0. Now by static 0 glitch, we say that the signal X, which is going through one path, and the not of X, that is the path where there is an inverter, and they are converging to an AND gate, it will lead to a static 0 glitch. So we can conclude that the static 0 glitch as an expression, or can be boiled down to an expression of X and it with not of X. So a signal converging at an AND gate with its you can say negation can create a static 0 glitch. On the similar lines, there is a static 1 glitch. By static 1, it means that the value should be held its value stable at 1, but it momentarily goes to value 0. So here we can say that the signal is converging at an OR gate with its negation that may create a static 1 glitch. And the expression that can be reduced to identify the static 1 glitch is something like this: X odd with not of X. The third type of glitch is known as the dynamic glitch. By dynamic, it already meant that the value is changing not only once, but more than one. So here the signal X is changing value more than one and then going to its steady state value. Dynamic glitch itself has a static glitch in itself. So here you can see the upper two paths are combining to create a static 0 glitch. And now there's an additional third path, which will introduce some kind of delay and which are converging at an OR gate to introduce a dynamic glitch. So the expression that can be understood to that can be written to understand the dynamic glitch is something like this: there is a static 1 glitch that is combining with some other third path to create a dynamic glitch. Similarly, a static 0 glitch is combining to some other path to create a dynamic glitch. Okay, so any combinational logic that can be reduced to any one of the above can cause a glitch. So our aim is to identify the combinational logics, do some analysis and see that they can be boiled down to this kind of expression or not. If we are finding this expression, then it means there is a glitch. Okay, now this slide, we are going to represent you how a synthesis does optimization and create a combination logic that can cause a glitch. So here there's a schematic. The figure 1 represents a schematic for the RTL of a demux crossing. Now this crossing is considered safe at the RTL. Okay, but after synthesis, it may happen that the synthesis tool creates this logic for the AND gate and the mux into this kind of logic. Now this logic that was done after the synthesis, after we get at the gate level design, after the synthesis step, here we can see that if the TX1 is at L value 1, so this is at 1, and my select line, the demux crossing select line, that is the enable path, or you can say enable logic, is held at value 0. You can see that this AND gates output are written down over here. So the first expression will give us the TX0. This two will give us 0, and the third AND gate will give us not of TX0. And these are combined at this OR gate to give us the final expression of TX0 odd with not of TX0. And we already concluded that whenever there is an expression that reduces to this kind of expression, X plus not of X, this introduces a glitch in the path. So what we are saying is that the RTL that was safe during the RTL sign off, but due to synthesis, it may create the logic or combination logic that can introduce the glitch in the design at the gate level. So synthesis can break the corrective circuitry or may add surprise paths. The mux that was used as RTL for CDC crossing now introduces a glitch. Synthesis tool may implement combination logic which introduces glitch. So this is how we identify the glitch. And this glitch can be a potential reason for the chip failures. So this we have seen on the CDC path. Next, we are going to show you on the clock and reset paths. So there's a reset select example. So simple multiplexer with a select line, and this can be, there can be two resets. Let's call them A and B. Now these are going to the reset pin of a register. After synthesis, it may happen that it simply reduces this multiplexer to this kind of combination logic, where there are two AND gates and that are combined into an OR gate. So if the resets, or you can say A and B, are held at value 1, we can see that the expression that it boils down. So here it will propagate the cell as it is, and here it will propagate not of cell, and these are combined at an OR gate to create an expression of cell plus not of cell. Now this creates a static 1 glitch, and which can cause unexpected resets at this flop. So a simple multiplexer in the RTL after synthesis may create some combinational logic that introduces a glitch. And this can be problematic for both synchronous and asynchronous paths. So we already seen that this glitches can cause unexpected resets and may put your design to a reset state, or it may introduce unexpected clock edges, which will introduce the dynamic power dissipation of the design. Okay, here I've just shown you the second, you can say a different kind of synthesis. So you can say that you can tweak your synthesis tool to, you can say, offset some constraints, so that now this synthesis gives us this kind of combinational logic. So after tweaking your synthesis tool, it may happen that this multiplexer is now reduced to this kind of combination logic. Here, if the value of cell is at 0 and A is at value 1, so it may happen that B will introduce a glitch on the reset path. So the expression that reduces is B plus not of B. Again, a static 1 glitch on the reset path, which can give unexpected triggers of the resets. Okay, so from this slides, we conclude that after synthesis, the logic that was safe at the RTL may introduce glitch issues at the gate level design. Now, what are the, you can say, existing methodologies or methods that are, you can say, that are used to detect glitches? The first one is the simulation. So for each of the clock or reset paths with combinational logic, the receiver value can be sampled in a gate level simulation. Sampled values then can be used to identify the presence of glitch in the path. Due to the asynchronous nature of signal paths, many simulators have difficulty sampling this signal paths. At times when glitches may be present. Even if the simulator catches a glitch path and a waveform is present, it is difficult to manually identify the source of the glitch path. So we are left with a waveform that says there is a glitch, but we do not know where is the glitch source. And since gate level simulation takes a lot of time, it's not exhaustive. So this approach, maybe you can say it's very difficult to use. The next approach that verification engineers use are the assertions to identify glitch. Some verification engineers have elected to write assertions to check if the simulators are sampling the signal paths at the correct time, but the results of sampling checks are often not accurately captured by the simulator. Assertions also have some semantic limitations when it comes to asynchronous clocks or resets, and all simulators may not be able to handle this kind of assertions. So writing assertions may itself become a difficult task. The next approach is of the static checks at a netlist level. So what verification engineers do here is basically they also perform static checks on the circuit design to identify the portions of circuits that may be susceptible to inducing glitches and signals traversing a clock or reset path. These static checks typically include flagging every clock and reset signals that contains combination logic in its path for manual inspection. So while we say that while manual inspection can identify the combinational logic capable of introducing glitches, the procedure is itself error prone and time consuming. This becomes a mammoth effort at the gate level. The presence of design for test, that is a DFT logic or the power logic, also makes the relatively simple RTL more complicated. So these approaches that are used for detection of glitches are very difficult. The next is we are representing you our methodology. This methodology employs, you can say, static analysis on the expressions and formal analysis to prove whether the glitch is propagating or not. So we are going to explain you step by step what this methodology means and how it's better than the existing methodologies. Okay, so our methodology is being divided into 5 parts. The first one is the design setup. For design setup, the gateway will design initial constraints should be provided. The initial constraints file consists of information about the top level clocks, resets, designs, design modes, constants, etc. So as you can see, we have written here the RTL constraints. So we are using the existing RTL constraints that you use for your RTL sign-off. So using a transformation engine, we transform this RTL constraints to the gate level constraints, and we do the we come to the next step where we detect the clock and reset paths. So the next step is of the clock and reset paths. Identification of clock and reset trees happen in this step, and we mark all the registers in the design with corresponding clock and reset domain. So this is done in the CDC analysis. So here we do the gate level CDC analysis and identify all the clock and reset paths and mark the registers with their corresponding clock and reset domains. So since we do not require the gate level constraints and we are using the existing RTL constraints, this saves us a lot of amount of time. So we also use the same transformation engine to apply waivers that were used at the RTL sign-off. So this is an automated engine that is integrated with the Questa GCDC tool. The next step comes the major step in the detection of glitch. So this glitch analysis step is basically broken down into 2 steps. First is the static analysis related to glitch, and the second is the formal analysis. So let's first discuss about the static analysis. In this stage, it innovatively identifies the unique glitch-prone combinational expressions common to many clock or reset paths. So let's say we have multiple registers that are driven by same combination logic. Now we identify this unique combinational logic and then do one comprehensive expression-based analysis on this combinational logic tree to identify the potential glitch candidates that can cause glitch to propagate. So once we identify this potential glitch signal, we do formal analysis on this. In the formal analysis step, the glitch list is further pruned. The potential glitch list is further pruned to identify the scenarios under which the glitch really propagates to the receiving nodes. To accomplish this, we utilized formal engines to verify the glitch propagation conditions and conclusively give counter examples of scenarios under which the glitch will propagate. The counter example helps the verification engineer convince the IP team of the exact scenario under which the glitch can propagate and cause a silicon failure. So this is all about the glitch analysis step. So here we detect the glitches on the CDC paths, clock paths, and the reset paths. Debug it. So we provide you debug it in terms of a schematic for the glitch signal. So here we show you the glitch signal, the converging point at which the glitch converges, and the receiving node. We will discuss more on this, how this debug helps in reducing the turnaround time for the glitch detection and glitch sign-off. So once you fix the glitches, you're ready for the CDC clock and reset sign-off. So this tells you about the methodology where we use the existing RTL constraints. We provide you proper debug aids for quick glitch closure, glitch sign-off, and also it's not time consuming as it's done on the static it's using the static expression based analysis. Okay, here comes the results that were on the designs that were that employed the methodology that we just introduced to you. So the first slide tells you about the clock glitch results. So we have run the methodology on 2 designs, 2 actual designs. Let's call them design A and design B. design A has around 10 million gates and design B has around 2 million gates. So here the point to notice is that the number of glitch signals identified are 3, but the clock paths impacted is 1. So it may happen that a particular receiving node may have more than one glitch signal impacting it. So here is one glitch signal, but it may happen there is another glitch signal that is going to the same combination logic or the same path and to the receiving node. So it may happen that a single path may have multiple glitches. Okay, the next slide is on the similar design that used for the glitch to identify the reset glitches. Here also we have the 4 reset paths, but have 6 glitch signals. So it may happen that more than one glitch signal is impacting a single receiving node. So this is complemented along with the proper segregation of results. So we also segregate the glitches based on their criticality. So for the reset glitches, we classify them as the one that can give unwanted triggers of resets to the flops as more critical. So there is a segregation on the basis of the criticality for the reset glitches. Okay, now the coming slides will talk about how, with the help of the proper debug gates, how we reduce the turnaround time for the glitch sign-off. Okay, so here is a snapshot for the glitch result report. So here we represent the glitch signals, the total number of glitch signals that are there in the design, and how many paths they are impacting. So here there are total 3 glitch signals that are impacting 2 reset paths. So here you can see a single receiving node. There is UD_3.q. UD_3.q is having 2 glitches impacting to it, A and B. So we report the glitch converging point and the destination register. We also report the possible glitch signals. So here there are 0 possible glitch signals. These possible glitch signals that are those which cannot be proven through formal. Okay. There is another section in the glitch report where we report the glitch propagation condition. So for the glitch source A to reach the receiving node, what are the glitch propagation conditions? So here are the signals and their corresponding values. So we report the glitch conditions that have been proven through the formal analysis. Okay, next comes the glitch schematic. So we give you the debug gate for analyzing the schematic to see whether it's a glitch signal and what is the converging point and what's the receiving node. Along with that, we also give you the glitch propagation conditions. So here we have seen that this is UD_1 3.q. So this is my receiving node and this is my glitch source S. So here the glitch propagation condition is that B should be 1 and A should be 1. Here we represent that in the schematic. Okay, to summarize the methodology. So what we do is we intelligently identifies the unique paths which are glitch prone and perform an automatic formal based glitch analysis to improve the quality of results for glitch detection. This in results ensure that the glitch reported from noise and gives proper debug gates on the details for the glitch source and the converging point. This methodology identifies a few relevant proven glitches and helps user focus on verifying them effectively. The generation of counterexamples under which the glitches would actually propagate makes it obvious that the reported issues are genuine and pose serious threats to our next SOC. Advanced debug techniques that highlight the glitch introduction point help in fixing the glitches efficiently and reduces the verification cycles and respins. So that's it. Thank you. Thank you for attending and showing interest in this session.
Okay, thank you for your presentation. If there are any questions, please use the chat. Okay. Okay, if not, then thanks again and some applause for your presentation. And yeah, then let's wait 4 minutes before we start with the next presentation.
Thanks.
Thanks a lot.
So, Karsten?
Yeah.
So the next presentation is mine. Do you want me to do it live or use the record?
I would like to do it live, but we can also use recording like you
Okay,
like.
I'll use a live presentation.
Live presentation. Okay, yeah, thanks a lot.
So I'll share my screen then.
Yeah, maybe you can try to share it. Then maybe people will see what's the next session. Then that's good. Okay, yeah, I can see your screen here.
Perfect. So for the interest of bandwidth, I will keep the camera off, but I'll switch it on when the questions part come up.
Yeah, that's good. Let's wait for 2 minutes so that maybe people join from another session.
Sure.
Okay, then let's start with the last presentation of the session. Then it's from Sarmad. If you have any questions, please use the chat, and then after the session, after the presentation, then we can or Sarmad can answer these questions. Okay, then Sarmad, please start.
Thank you. Hello, everyone. My name is Sarmad Dahir. I'm a principal application engineer from Cadence Design Systems based in Stockholm, Sweden. I and my team support many different tools, including verification and high-level synthesis, among other technologies. And I'll start with a very short story from my background. So during my career, I found myself several times in a situation where a project was forced to tape out before verification reached 100%, because we couldn't afford to wait, and we had to take the risk. But things have changed, and in this presentation, I'll tell you about the solutions we have today that I wish that we had back then. So today, this presentation, I will explain how high-level synthesis design methodology can help from the design for verification aspect for multi-pipeline designs. In modern hardware designs nowadays, a significant part of the data processing is done in specialized hardware instead of software. Therefore, we have complex designs with multiple pipelines, and this is very common nowadays. Hardware design architecture decisions like how to access shared resources, for example, memories, make a big difference on the overall performance of the system. This increasing hardware design complexity also add verification challenges on the verification teams. For this paper, we prepared a example design which has it's a multi-pipeline design with resource sharing to explore different available solutions. It's a pipelined fear filter design, and the produced data is stored locally on an on-chip memory. The data can be accessed externally from downstream modules in the system using a dedicated read interface as well. This design requires as you can see there, a memory arbiter unit that can receive memory access requests from multiple pipelines on every clock cycle. So if more than one pipeline issues a memory access request at a given cycle, the higher priority pipeline is served while lower priority requests from other pipelines are rejected. The arbiter is required to signal back the response, whether it's a acknowledge, an ACK, or a NACK for every memory access request to the initiating thread or pipeline. So to overcome the increasing design complexity, the concept of design for verification is usually applied, and we will look a little bit closer at what that is. Design for verification invites designers to think about the ease of verification during the design implementation phase, meaning while planning and developing the design code itself. In complex pipeline designs, bugs can be hidden deep inside the logic, and they require a very specific set of stimuli to expose them. Bugs could also be caused by ambiguous specs. If there's anything unclear in the specs, this would lead to faulty assumptions on the target or needed functionality of the design. So design for verification principle was thought of to aid the verification quality and efficiency and also capture design bugs faster. In general, to achieve better design for verification, designers can add additional hardware to access some design internals and examine them, which adds more visibility for verification purpose. So imagine you have a subsystem where you have a CPU attached to a bus on one side, and from the other side of the bus, you have few slaves. So if you, in each slave on its base address, you put a register, which is an ID register, that is a unique number that representing the type of module and some revision number, for example. So verification will be much easier by just doing a loop on the CPU or the master interface that just loops on all the base addresses, reads this ID register to check that the correct module was instantiated at the correct connected at the correct port of the bus, and it's of the correct version as well. So you simply add a little bit more hardware, and you gain much more ease of verification by doing that. The second point is if you use higher level of abstraction for algorithmic code development, this makes the debugging and verification of algorithmic functionality much easier. And you also can achieve better design for verification if you speed up your simulations, because that will give you faster turnaround time. Applying early coverage analysis allows for obviously finding issues much faster. Augmenting simulation with other automated technologies, for example, formal verification, allows for finding issues with minimum additional effort. And of course, it's always good to make it a habit to use assertions in design code to highlight illegal scenarios or conditions or corner cases to the verification teams so they can focus on them and verify them. And also to highlight the assumptions made by the designer on the design spec. So now let's consider how high-level synthesis methodology fits into this topic. In general, high-level synthesis accelerates the RTL design and implementation and optimization phase. HLS designers are focused on writing abstract algorithmic system C code and then let the tool deal with low-level implementation details like building state machines, pipelining, partitioning, and etc. The tool can be configured to optimize the produced RTL for different targets, like you can, from the same system C source, you can generate RTL1, which is for low power. You can generate RTL2 version, which is for low area, or RTL3, which is for high performance. So you have much better code reuse, and then you can retarget the same IP for different applications. HLS also has features that aid the design for verification aspect, which we are looking at here. So to implement our example design using Stratus HLS, we have a first system C thread that implements the fear filter logic, a second system C thread that handles the data read IO requests from the other modules in the system, and the third system C thread that implements the memory arbiter logic itself. All of these three threads are pipelined with initiation interval of 1, meaning that a new iteration can start on every new clock cycle. We chose to do the communication between these threads and the arbiter using FIFO pairs. These are the request and acknowledge FIFOs. The request FIFOs are used for sending a memory access request to the arbiter. The acknowledgement FIFOs are used for signaling back the request status from the arbiter. When using HLS for design, the input implementation by the designer to the tool is a behavioral system C model. This model is at higher level of abstraction and faster to simulate than RTL, and it's easier to debug as well. It can be used in hybrid verification environment where we can switch the DUT instance between RTL and system C at compile time. To achieve this, we need this model to match RTL in two things. The first thing is the IO pin layout. So you can, using the same, just change the instance inside your system and just switch between system C and RTL because they match in pin layout on the entity. And the second point is the simulation timing behavior. To achieve this, the system C coding style needs to be done with some consideration. The simulation timing point that I mentioned in the previous slide is because in RTL, you have a real pipeline where the thread loops iterations are running concurrently. In behavioral system C, there is no pipeline. Loop iterations are running sequentially. Each put and get function calls to send or receive data consume one cycle each. So we basically run at an initiation interval which is greater than 1, as you can see in the picture here. This would cause simulation mismatches compared to RTL simulations if your system is timing sensitive. To get matching behavioral system C and RTL simulation, we changed the system C coding style a little bit to make the simulations match. So the put and get functions are replaced with non-blocking versions, so they don't consume a simulation cycle. Also, we pull on the IO ports and the FIFOs to check who has an item to transfer. This picture shows the pseudocode of the 3 threads or loops with the non-blocking communication. So the functionality here is unchanged, only the coding style changed a bit. And this way, we start a new loop iteration on each new cycle, even in the behavioral system C simulation. So we can do a new IO input handshake on every new cycle in system C simulation, just like in pipelined RTL. When it comes to assertions, in high-level synthesis, the design input is behavioral system C. So the designer can add assertions in the system C code. The question is, how can the designer add assertions in the generated RTL to communicate illegal conditions to the verification team? The answer for Stratos HLS users is to enable the assertion synthesis feature, so system C and C++ asserts are synthesized into the produced RTL. In this picture, you can see the SC assert is synthesized into RTL, and verification teams can easily see it and collect coverage on it in their verification environments. The assert message has a reference to the originating system C source code line, so it can easily be traced back to the originating source. Early coverage analysis could reveal many findings. One of the simplest and most basic coverage variants is line coverage with GCOF for system C and C++. In our example, when we turned on the line coverage for our design, we were missing one single line in coverage results. By just opening the system C coverage viewer in Stratos IDE, we could see that we never had a memory read from the high priority thread. It's the red line highlighted there. So this could either be a missing test case to be added to the verification environment, or a design bug or error if this thread is supposed to do only writes and no reads are allowed. So in a simple click, you can make very interesting findings. These are, seconds really well spent. And the options that you have there, if you don't like GCOF, of course, we have integration with Bullseye, which offers also some more sophisticated coverage analysis like condition coverage. If we keep on the coverage closure aspect, the verification quality and efficiency could be enhanced by augmenting simulation-based flow with other automated technologies like Jasper Gold formal unreachability app. This way, we can discover unreachable code using code coverage analysis without spending any time on writing and debugging new test cases and running simulations. Reachable coverage holes are usually potential missing tests or improvements to the verification environments. Unexpected, non-reachable, all reachable code could be design bugs. Tracing back uncovered RTL code to originating system C source is straightforward in Stratos HLS by enabling the RTL annotation feature. As you can see here, the uncovered coverage hole can easily be traced back to system C source using the RTL annotation feature in Stratos. In this picture, the IMC coverage viewer is used to analyze the code coverage results. And the 0% that you see in the picture, that's the missing line coverage in the RTL. And if we just look at the annotation, the comments inserted by Stratos, we will see that this line or this part of the code came from the dut.cc file line 139. So by looking at that file, it's much easier to debug and understand the functionality. This saves weeks of verification effort to identify weaknesses in the test bench or possible design bugs. This also allows developers to debug the design logic in its higher abstraction representation instead of debugging complex RTL pipelines. The results from our example design are: we could see more than 3x simulation speed up with System C behavioral model compared to RTL simulation. The System C code is much smaller. It's only approximately 3.5% compared to the RTL code, which makes it much easier to debug. Assertions were synthesized into RTL by simply enabling it in the tool. It's basically just flipping a switch. And it was easy and straightforward to integrate with Jasper Gold, and findings were very useful to identify missing verification tests or potential design bugs. The RTL annotation feature that I showed earlier made it very trivial to trace back uncovered code to System C source, where it's much easier to debug. And this feature in general is very useful if you have a piece of RTL which is hard to understand and you want to understand where this came from. Then the RTL annotation could take you back to the System C source, so it's easier to understand the functionality in there. So as a conclusion, we could see that high-level synthesis design methodology had a positive side effect, where it also helps achieve better design for verification. HLS is designed for keeping focus on abstract algorithmic code, which is easier to verify, and it also offers shorter simulation turnaround time. Issues and faulty assumptions could be captured early with the coverage analysis capabilities on different levels of abstraction, and high-level synthesis allows designers to easily make use of automated formal techniques like Jasper Gold UNR to discover issues much earlier. Stratos HLS features like RTL annotation and assertion synthesis adds visibility and makes it very easy to shift most of the functionality debugging to the behavioral System C code instead of RTL. All the suggested points to improve design for verification were met using the high-level synthesis methodology. So HLS in general lowers the risk for finding bugs late in the project and risk missing time to market goals. Thank you, and I'm happy to take questions now.
Okay, thanks a lot. Is there any question? Please use the chat if you have questions. Okay, if not, then I should remind you to vote for the best paper award and best poster award. I think there's a link available for this. Okay, then thanks for attending the session, and yeah, hopefully we see you soon or next year in real life. Then. Have a nice day then. Bye.
Thank you. Bye-bye.